Sprawled across North America, from the polar ice cap to the Mexican border, is a giant with 1,000 eyes. Day and night, fair weather or foul, he guards his homeland. This giant is the air defense system of North America, a vast and intricate maze of radar networks. And through the electronic eyes of this giant, we are able to see the enemy before the enemy sees us. These radars never sleep. Round the clock, they stand ready to do their part in minimizing the penetration of enemy bombers. And round the clock, their quietly pulsing hearts, the magnetrons and the Klystrons, help generate the power for peace that keeps America strong. These microwave power tubes, the magnetron to generate the radar signal, the Klystron amplifier for radio communication, and radar are the subject of our story. It is a story about these vital tubes, but even more about you, the men who work with them. When you have a well-trained maintenance man with a well-adjusted radar at a well-chosen site, then you've really got a winning team. They keep the airborne radars operating and ready for crucial missions. In missiles that depend upon radar for guidance. In bombers that depend upon radar for bombing and navigation. In interceptors that depend upon radar for fire control. And in reconnaissance and search aircraft that depend upon radar to extend their vision. Years of scientific research and millions of dollars worth of equipment have gone into this aircraft. But only if the maintenance men keep the radar functioning can it complete its mission. When something goes wrong, they've got to make a quick decision, whether to attempt repairs in flight or abort the mission. There's trouble here, that's for sure. But what kind of trouble? First, they check the radar scope presentation. Sometimes this gives a clue. But the most reliable analysis comes from the test equipment on the monitor panel. The spectrum analyzer shows them the conditions in the circuit. It tells them what part of the equipment is malfunctioning and helps trace the cause of trouble. Here's the RF spectrum waveform. The output pulse of this radar transmitter is definitely abnormal. This is the way it ought to look. But this presentation clearly shows a disturbance, probably caused by arcing in the antenna waveguide. The cause might be moisture in the waveguide, corrosion, dents, or scratches. Another trouble spot could be the pressurized antenna system. Loss of waveguide pressure will also cause arcing. Yes, the pressure's low. This is a danger signal. If this arcing continues, the magnetron output window may be damaged, the tube's vacuum lost, and the magnetron destroyed. Waveguide joints should be tested to make sure they're airtight. This man is making a liquid soap test. See where the bubbles are forming? He's found the trouble. But how serious is it? He checks the spectrum analyzer again. It looks bad. See how the pulse has changed? Finally, the main pulse deteriorates completely. Bad news. The magnetron is seriously damaged. It's beyond repair. This means shut down the equipment and get ready to install the spare. While they're working, let's take a look inside the magnetron. Animation shows what caused the malfunction. We'll turn time back a few hours and show the Maggie functioning normally. As the pulse from the modulator is applied, the Maggie produces radio frequency oscillations to form the radar pulse. This energy is then coupled into the waveguide and directed to the antenna for transmission. Energy is reflected back along the waveguide toward the magnetron. Normally, when the antenna system is in good shape, the reflected wave won't be strong enough to cause arcing at critical points. But as conditions such as loss of waveguide pressure develop, the antenna characteristics change and the reflected wave becomes greater. Then arcing may take place at the point where the radar wave leaves the magnetron, causing the magnetron output window to crack or puncture. As the vacuum is lost, the heater oxidizes and burns out. The cathode cools. Air seeps into the interaction space, and arcing occurs with each pulse. After the magnetron has been unbolted, the filament and cathode connections are uncoupled. A large magnetron like this one requires 2 men to handle it safely. Before a Maggie is replaced, all connections, mating flanges, and sealing surfaces should be inspected. Insulating oil should be examined for foreign matter. Damaged or worn gaskets should be replaced. Heater's supply voltage should be established at the value marked on the tube. Later, when the plane returns to base, the heater voltage should be double-checked with an accurate instrument. Now that the spare magnetron has been installed, further tests are necessary. The technician must make sure he has the required pressure and that there are no air leaks. Instructions concerning the care of pressurized antenna systems will be found in the appropriate tech order handbook. The liquid soap method is a simple way to check for pressure leaks and may be used where more accurate means of testing are not available. Test equipment is used to analyze the performance of a newly installed tube. The output pulse is checked on the spectrum analyzer. See how the large hump or main bang is symmetrical and sharply defined. The side lobes are relatively small. A presentation like this means that the Maggie is firing properly. Not only that, it means that these technicians know their jobs. They were able to analyze the trouble correctly and replace the magnetron in flight. Because they knew what to do, this aircraft was able to complete its mission. Let's take a closer look at these microwave power tubes. Magnetrons costing from $100 to $10,000. Klystrons costing from $1,500 to $25,000. Why so expensive? Let's see what's inside them. Look at this. Parts so critical, they must be inspected through a microscope. Tolerances accurate to 4/1000ths of an inch. To build them to such close tolerances requires involved manufacturing processes. Specialized parts must be carefully assembled. The completed assembly is heat treated to bake out gas molecules. So that they may be removed by an evacuation machine. External mechanical parts, such as couplings and magnets, are installed. The final step is rigid testing of electrical performance to make sure it meets the high standards required. Pressure tests ensure leak-proof connections throughout. Now the tubes can be put into storage. Even here, should tiny defects develop while on the shelf, continuous sample testing will reveal them. Before shipment, the delicate tubes are carefully packaged. The quality designed in during research, built in during manufacture, maintained by rigid testing and careful storage, will reach the user intact. Here are a few basic rules on proper handling. Always use 2 men to lift a heavy tube. A portion of a carton makes a good tube stand, protecting delicate parts from damage. But a wooden rack is better and lasts longer. Save all the cartons and packaging materials. Use them to return defective tubes to the factory. Magnetrons should be separated at least 12 inches. Then their magnetic fields won't interlock. Don't store them on steel shelves or they may be degaussed. Don't use steel tools. Use non-magnetic tools. Following these simple rules will save time and trouble, prevent damage, and save the Air Force many thousands of dollars each year. On most of the smaller high-performance aircraft like this one, it is not possible to do in-flight radar maintenance. Therefore, most of the work must be done in the electronics maintenance shop. This aircraft has just aborted an intercept training mission. The reason, radar malfunction. Had this mission been the real thing, an enemy bomber could have broken through our defenses. The maintenance man's job is to find out why the radar malfunctioned and correct the trouble. You'll see that although these radars come in smaller packages than those on larger aircraft, they are just as big a maintenance problem. The maintenance supervisor is in charge of this work. Before teardown of a defective black box is started, the operational defects should be identified or at least isolated to a particular subchassis. The pilot's report on the radar failure may give a clue. Comparing the report of malfunction with equipment handbooks may also help to isolate the defect. But the best aids to repair are the analytical approach of the technician and the special test equipment he uses. An important point to remember is that the transmitter malfunction may be caused by parts other than the magnetron. Wherever possible, other circuit components should be checked before power is applied. A simple resistance check will often reveal a short circuit. That's what the trouble is here. The airman will carry on from here and trace the short circuit. So far, so good. He's found a shorted filament transformer and replaced it with a new one. But what's this? He's decided to change the magnetron, too. The supervisor disagrees. Tube swapping is not a good idea. The old magnetron should be thoroughly tested before any decision is made. Testing showed that the old magnetron should be replaced. this has been done. Now let's see how the new Maggie behaves. This is confusing. The spectrum analyzer shows arcing. Let's look inside the tube and see what's causing it. Magnetrons are made of porous metals, which usually trap a small amount of residual gas. During storage, gas molecules migrate into the interaction space surrounding the cathode. When the tube is installed and power applied, it will operate normally if the gas content is low. But if gas content is high, arcing will occur with each modulator pulse. This arcing might be mild or severe. Frequently, tubes with residual gas can be restored to normal operation by a suitable break-in or seasoning period. During break-in, the gas molecules are driven back into the walls of the tube, and normal operation resumes. If the equipment is operated frequently, normal operation should continue throughout the life of the tube. Occasional individual arcs may also be noted in a normal tube which does not contain gas, but this behavior is due to transient conditions and should be considered as normal. All new tubes which display arcing when they are first installed should be thoroughly tested and analyzed before being discarded. This will save the government both time and money. The repairs are finished. Now comes the break-in procedure. Proper break-in can clear up various degrees of internal arcing. But watch the spectrum analyzer carefully. If frequent arcs occur, switch to standby immediately. Small magnetrons may be damaged if severe arcing is allowed to continue more than 2 seconds. Now the range selector switch must be changed to short pulse before the magnetron is operated. If only sporadic arcing occurs, the operation may be continued. But a series of arcs may cause the overload to pop. In this case, reset the switch and continue the break-in. To avoid possible damage during the break-in, the technician should keep a close watch on modulator tubes and other components of the RT unit. The time required for break-in will vary with the tube, conditions, and methods used. But normally break-in can be accomplished in 20 to 60 minutes. When break-in is complete, and only infrequent arcs or misfirings occur, operation may be regarded as normal, and the equipment made ready for service. In addition to the airborne radars, there are a great many ground radar sites scattered about the continental United States and Canada. They are found in almost every type of American scene. In the dusty expanse of the plains, in the northwoods, the heat and humidity of the deep south, in the rolling farmlands of the Midwest, and the saltwater scenes of our coastal areas. Each of these has its own problems of maintaining and efficiently operating its microwave power tubes on a round-the-clock basis. Some of this equipment is completely automatic. But experienced technicians are always nearby, just in case. At the many radar sites where there is no standby equipment, the maintenance man is an even more vital unit in the organization. In the operations room, observers keep constant watch on the radar scopes. Here's trouble developing. When equipment starts to malfunction, quick repair is a must. These men are so used to the sound of the equipment, they can tell by listening whether the magnetron is operating or not. It's not. Something caused this radar to quit. What was it? Sometimes the meters will tell the story. The filament current has dropped to 0, and the filament voltage is too high, indicating that a portion of the heater element is open. A quick, careful analysis has to be made. Here is where maintenance skill and training pay off. The question is, has the magnetron become inoperative because of heater failure? Or is there another cause? Yes, here's something. The insulator is pitted. High-powered magnetrons like this one have insulator bushings immersed in oil. It might be that the insulating oil has broken down. Better check this. Here's the answer. Contaminated oil. The oil failed to insulate. Oil can break down after long exposure to heat and high voltage. Oil may also be contaminated by dust, moisture, metal particles, or air bubbles. Here is how contamination breaks down oil. As contamination accumulates in the oil, current paths are created between high voltage terminals and ground. As the condition becomes worse, due to increase of contamination and change in oil structure, a definite high voltage path for corona discharge is created in the oil. The corona discharge begins to erode the surfaces of the insulator. As the insulators are penetrated, the vacuum in the tube is destroyed, and the tube is damaged beyond recovery. The maintenance men have completed oil replacement using all precautions to prevent contamination. They have checked the grade of oil against tech orders and factory instructions. But before installing the new Maggie, all mating surfaces and flanges must be inspected and cleaned or replaced as required. It is also necessary to check waveguide parts, replace gaskets, coolant hoses, oil fittings, and so forth. Be sure all electrical connections are secure. Careful, watch out that terminal doesn't hit the cabinet. That could ruin the tube. Make certain that all clamps, bolts, coolant hoses, and so forth are secure before operating the tube. All set? Okay, hit the power button. Uh-oh, that one didn't last long. There are many reasons why new tubes may fail to function properly. One of the primary causes of tube failure is damage sustained during transportation and handling. This damage may occur during shipping or in the depot. Or during Air Force distribution to the base. Here is what actually happened to that new tube which failed to operate. Nobody saw it happen. Nobody's going to tell. And nobody's going to get the slightest use out of that magnetron. But these men don't know this Maggie fell off a truck. They just know it won't work. Could it be something wrong with the rest of the equipment? A short circuit? A bad connection? Or should they pull out this Maggie and install another? They've installed another new Maggie. They've also followed correct procedure, allowing the heater to warm up 5 minutes before applying power to the anode. Ah, it works. But wouldn't it have saved them a lot of time and trouble and expense to the government if that delivery man hadn't dropped the Maggie off his truck? You see, the maintenance man really is important. If he does his work correctly, so will the radar. The Magnetron is only one type of microwave power tube used by the Air Force. Another and very important type is the power Klystron. Klystrons are made in many shapes and sizes. All of them are powerful and expensive, all the way from $1,500 to $25,000. Let's look inside a typical two-cavity power Klystron and see how it operates. The beam current is emitted by a heated cathode and passes through the drift tube sections. Since electrons in the beam have like charges, they repel each other and tend to diverge, to be absorbed by the walls of the drift tube sections. But electromagnetic coils placed along the tube align them into straight paths. However, misalignment of the focus coils can seriously damage the drift tube tips. Therefore, it is most important to adjust the magnetic coil currents properly during installation of the tube. When a steady direct current is flowing through the tube, an RF signal from the RF driver stage is introduced into the first cavity resonator. As the cavity is tuned to resonance, a strong RF field appears between the drift tube tips, which form a gap in the resonator. The electrical charges on these tips alternate at the driver frequency rate on opposite sides of the gap. At the same time, individual electrons in the beam are being accelerated or decelerated at the RF frequency rate. This produces bunching of the electrons as they approach the gap in the second resonator. There they are decelerated and release energy. The resonator converts this energy to RF energy and amplifies it. Additional resonators are sometimes provided for greater amplification. From the last resonator, the amplified RF signal is coupled into the waveguide and transmitted to the antenna. Various kinds of Klystrons are being phased into new Air Force applications, such as these tropospheric scatter communications transmitters. In this way, intelligence may be relayed from remote early warning sites to control centers many hundreds of miles away. This transmitter has dual equipment. One transmitter operates while the other is on standby in case of emergency. The equipment is automatic. Meters and instruments keep a constant check on its operation. And a warning light flashes in case of trouble. And speaking of trouble, a glance at the meters tells them the trouble is in the transmitter output. The equipment is reoperated. Readjustment of the output cavity and coupler may correct the trouble, but the arcing continues. Since adjustment won't correct the trouble, all they can do is shut down the transmitter for repair and switch over to standby. The Klystron has been removed for inspection. It may have been damaged by the arcing. Yes, the output ceramic is badly damaged. An important consideration in maintaining the Klystron is the proper adjustment of the impedance matching unit. In this case, improper adjustment of this unit during installation ultimately caused the arcing in the output section which in turn destroyed the tube. There are two types of meters which help maintain proper coupling: the power output meter and the VSWR, or voltage standing wave ratio meter. These measuring devices should periodically be checked for accuracy. But in general, the best way to avoid damaging or destroying the Klystron is to study and thoroughly understand the various installation and operating instructions furnished by the equipment and tube manufacturers. Only by doing this can the Air Force technicians and maintenance men hope to get the full operating life from their Klystrons. At the Tropo Shack, the maintenance men have installed the new Klystron. But before operating at full power, they are careful to recheck all circuit meter readings and coolant flow gauges. These meters are important because a minor error in one of the adjustments might shorten the life of the tube. The power Klystron is really a very dependable piece of equipment if properly treated. Once it has been correctly installed and aligned, it requires very little maintenance during its long service life. A good rule to follow is install it carefully, align it properly, then leave it alone. As the progress of aircraft and air defense continues, other and more varied uses will undoubtedly be found for microwave power tubes. With these new applications will come new problems to be solved by maintenance men of the future. Those men will tread the paths charted by technicians of today who found that this type of maintenance can be simplified by careful attention to four basic factors: careful handling, proper break-in, avoidance of tube swapping and trial and error maintenance, and the timely use of maintenance aids such as test equipment, tech order handbooks, and manufacturer's information pamphlets. There is no substitute for know-how, initiative, and ingenuity. Yet no one man or group of men can do this job alone. Maintenance is a team effort. Only by the cooperation of procurement, supply, transportation, and every department concerned can the Air Force continue to operate the reliable radar equipment which is such a vital part of national defense. Only by continued teamwork and devotion to duty can the radar eyes of America guide us to that peaceful tomorrow, which is the reward of nations who stay alert today and every day.